corrected your own work. So someone speak to me. How do I know it's a rational function? How do I know from looking at it that it's a rational function? It's in fraction form. Not only is it in fraction form, x is on the bottom, because this would not be a rational function, right? What kind of function is this? Linear, right? It's a linear with a slope of 3/4. So for a rational function, it's got to be a fraction, but it would have to look something like that, right? There would have to be at least an x on the bottom. Sometimes there's more than one term with x, so there's x squareds, there's x's on the bottom, but there's a variable in the denominator, which means most of the time, almost all the time, it means there's non-permissible values. Values that x can't take on, otherwise that would mean that the function itself, wherever that happens, where x is undefined, the function has asymptotes, right? Asymptotes are holes. So let's, I think you guys are comfortable. I hope that you're getting a little more comfortable with these. So what's the first thing that you would do in part E? In question E? Factor, right? So I think it's a -4 plus 3. I hope your factoring skills are improving if they were a little rusty at the beginning. Good. You find you're more comfortable now, Abby, with factoring? I'm gonna think it's probably an x minus 4 on the bottom and there's x minus 1. Perfect. So I get a common factor, which means there's a hole at x equals 4, right? My non-permissibles are x can't equal 4 and 1. Okay, so there's a hole at 4. What's the y coordinate where the hole is? Well, let's see. Let's look back at our statement, at our simplified statement, okay? And we put a 4 in where we see x. So that would be 4 plus 3, 7 over 3, wouldn't it be? 7 over 3, right? Okay, so that's where my hole is. That's important to know. What else? Is there a vertical asymptote as well? At x equals 1. Okay, the last thing horizontal asymptote. How about that? Let's see. Same powers of x, so y equals 1. So we're getting a lot of info here. Last thing's intercepts. X-intercept, y-intercept. Let's look at the top. If I do an x-intercept, if I put a 0 in for y, my denominator becomes not helpful at all. So my x-intercept would be -3. And that's not one of my non-permissibles, so that's okay. And my y-intercept, I put a 0 in for x, and I get -3, right? It's the same thing. Sometimes that happens. Okay, with all that info, I'm going to start graphing. So the first thing I'm going to do is I'm going to scheme my asymptotes, because for one of these, like it looks like it's kind of more of a traditional one. I'm probably going to get some wings out of here. The ones that you get with wings on them, your graphs will never cross the asymptotes. So first of all, I've got vertical asymptote at 1, horizontal asymptote at 1, x-intercept at -3, 1, 2, 3, y-intercept at -3. Oh, I guess I should have done this in a color, right? X and Y. Okay, I'm pretty confident I know what's happening down here, don't you? It's going to curve and it's going to bend, and the graph itself, when there's asymptotes involved, it wants to become the asymptote. It wants to look exactly like it and mirror image it. So it gets as close as it can and just starts running, not parallel, it actually keeps running closer and closer without ever touching. Okay, I just need to know what's happening here. Let's see, there's a hole at 4, and what would this be, 2 1/3? 1, 2, 3, 4, 1, 2 and a little bit. So there's a hole here, which kind of lines up. Now I could do another test point, right? But at least you have to do at least one, so I would be comfortable if you did that, okay? Good. That kind of had everything in it, right, Abby? All right, what about this guy? This guy should be easy. What do you know about him? Non-permissible value, x can't equal 2, and it's a vertical asymptote, right? At x equals 2. Is there a horizontal asymptote? Do you have more x's on the bottom than the top? So, y equals 0, right? Okay, how about x-intercept? Let's replace this with 0. So this disappears, so I get 0 equals 1. That means no x-intercept, right? Y-intercept, put a 0 here, so I get 1 over -2, -1/2. Okay? All right, so vertical asymptote 2. X-intercept is the other. Y-intercept is -1/2. And I think that's it, right? Okay, so I'm going to say that this section does here. Now, I'm pretty sure that this is just one of my traditional ones. I'm pretty sure my graph's up here, but I don't know for sure until I do a test point. So what value of x should I use over here? Yeah, anything greater than 2, right? Make it easy, so do x equals 2. So y equals 1 over 1. Okay, so at 3, 1, 2, 3, y is 1. Okay, so sure enough, that's it. That was an easy one, right? How about this one? What about non-permissible values? None, right? No value of x would make that undefined. No, there's no value of x that would make my bottom 0. Okay, so that's gone. So there's no vertical asymptote, no hole, no vertical asymptote or hole. Is there a horizontal asymptote? Yeah, y equals 0. Okay, what about x-intercepts? If I put a 0 here, the bottom disappears, so I have x equals 4, which is weird, even though that's an intercept, but that can happen for these weird ones. And I know it's weird because there's no non-permissibles, right? That's a really weird one. What about the y-intercept? Well, if I put 0s in for x, I get -4 over 2, so I get -2. Okay, so my y-intercept's -2. My x-intercept says it's 4. However, I have a horizontal asymptote. Now, that can happen with the weird graphs. And again, how I know it's weird is anytime there's no non-permissibles, it's not a typical rational. So what do I have here? This is definitely an asymptote, so the graph does want to act on it. So the only thing that could happen is it does cross here, but then it runs alongside it again. And again, if you checked on Desmos, that's what happens. This is all the info I have, so I'm pretty sure something happens over here. So you got to do a test point, right? I guess x equals -1 would be the smallest. So y equals -1 minus 4 over -1 squared is 1, 1 plus 2, -5 over 3. So that's a -1 2/3, so -1, negative about here. So it looks like it's heading up. Now, there's no other x-intercept, so there's no more crossing. So the only thing you can do is this. How many people got that one without looking at Desmos even? Did you? Good for you. Now, once again, this is very unusual that a graph will cross a horizontal asymptote. It'll never cross verticals. And again, the only reason I knew that this was weird is because of the no non-permissibles, right? That's your kind of little light that go on. Okay, let's do this last one. Someone else tell me the info. Just shout out I'm going to list out non-permissible values. Someone shout me out non-permissible values. 0, okay? So is it a vertical asymptote or a hole? I guess I should, can I factor it all, by the way? I guess I should do that, right? So I'd get x squared minus 2, right? Over x squared. Okay. It's a vertical asymptote, right? Because there's no common factor. All right, is there a horizontal asymptote? Someone shout out. Y equals 2. Okay, how about an x-intercept? Okay, so the bottom disappears. I guess I could do here. So I set this equal to 0, right? So 0 equals 2x squared minus 4. 4 equals 2x squared. X squared equals 2. So x equals positive or negative root 2. Okay, so that's my x-intercept, positive or negative root 2. Not nice, but it's a number. Okay, y-intercept, last thing, put zeros in wherever you see x's. So all we're left with is negative 4. Right? Okay, so what do I have? Vertical asymptote here. Horizontal asymptote here. Intercept, that root 2 is about 1.4, just a little less than 1.5. So here, 1.5, go here and here. And y-intercept of negative 4, 1, 2, 3, 4. Sorry? Oh, sorry about that. Yeah, thank you guys. Oh, because that's my non-permissible value, right? If I put 0 on the bottom, thanks, Joanna. No y-intercept. Got to take that out. Thank you. Okay, so what does this graph look like? What do I have here now? That would have been weird to graph it. I have a point here, and all these asymptotes. Pretty much this, right? Let's go back to that y-intercept. Yeah. I can't put a 0 in for x, right? Because I'd have x on the bottom. Okay. So that's another classic set of wings. Usually we see our wings diagonally, right? But this time the wings are side by side. That could happen too. It's still a function, right? All of these are still functions. This is the strangest looking one. Okay, so do you feel, I think you've been exposed on this sheet anyway to every type of, or most types of rationals that you could encounter, right? So I'll post.
White post, I think so. What are we going to do?
Horizontal asymptotes are allowed to be crossed. Yeah, it doesn't do anything, like look at, if I put the 4 in here, 4 minus 4 is 0, I get an answer for 0. That's okay if I get 0 on the top, just not on the bottom. Okay, any other questions so far about anything we've talked about with rational functions? No? Okay, we're done with the example booklet, but there's still a few things that I wanted to expose you to. And I asked you to read ahead a little bit on the rational equations, which is what I think you've actually worked with rational equations already, solving rational equations algebraically in grade 11, so it'll be a bit of a repeat. But what I want to do before that is I want to actually do one more style of rational equation that I think a few of you have seen already, and I've mentioned that we've seen them in a few examples, but they're of this style, this type of rational equation. 1 plus x plus 1 minus 2. Have you seen this style before? First of all, is it a rational equation? Why? X on the bottom, right? A variable on the bottom. So we haven't graphed these ones, and I'm going to show you something interesting, and then on the back we're going to do some rational equation stuff. So I'm going to give you one of these. So these aren't in your notes, and they're not in your textbook either for some reason. So I'm just going to give you style more. But what I want you to notice is, and I did mention this in class and in your notes, I think, this is our parent graph, right? This is how all rationals start, the 1 over x graph, correct? So it makes sense that we should be able to graph parent functions using transformations as well. And we can. Sometimes a rational function may be given to you in this form, for example. And as long as you recognize that, hey, the same rules apply for all the transformations, we can actually graph a rational function from this form, right? Now this would be the classic 1 over x one. The only graphs that we can transform using transformations are of this style, like 1 over x. There's just one x on the bottom. We wouldn't do it. You can't graph one of these using transformations, right? They have x squareds on the bottom. That's not the same parent graph. But if you just have one x on the bottom and then some adjustments to it, we can use our knowledge of transformations. Now, as long as you remember what the parent graph looks like, right? You have to always remember what 1 over x looks like. So 1 over x looks like this. Agreed? It's got vertical asymptotes of the axes of x equals 0 and y equals 0. So those are your asymptotes. There are no intercepts because I can't replace the denominator with 0, so no y-intercept. When I put a 0 in for y, like if I tried to solve for an x-intercept, I put 0 in for y, 1 over x. I cross multiply, I get 0 equals 1. When the x disappears, there's no x-intercept, right? And you get a nonsense statement, which is impossible. That means no x-intercepts, right? So we have no x, no y. This is what we look like. Jack, you want to come grab a paper? And then this is what I call a critical point. A critical point is 1, 1, and negative 1, negative 1. Now, that's not, there's only one critical point. I mean, there's more than that, but those are the critical points I identify in each section of the graph, right? So this is a different style of graphing. I just want to expose you to this in case you get a rational function in this form. So what would you do here? What do you recognize that the changes are, the transformations are? The transformations on the graph of y equals 1 over x, okay? This is my parent graph. What do your eyes make of the transformations from here to here? What do you see? What does that plus 1 attached to the x mean to you? Shifted, 1 left, and what does the minus 2 do? 2 down, right? Now, what would that affect on this graph? Well, it would affect everything, but these shifts affect asymptotes, right? So that means your asymptotes are shifted. That means my vertical asymptote will be, instead of x equals 0, my vertical asymptote will be x equals negative 1, and my horizontal asymptote will be negative 2, right? That's it. So that's one way you can graph. So now I'm just going to adjust my asymptotes. So here's my vertical asymptote. Here's my horizontal asymptote. Now I have my key points, right? If I want to do that approach again, my mapping that I usually do, I have 1, 1, negative 1, negative 1. I'm not sure if you need this, but x is shifted to the left 1, so I take 1 away. Y is shifted down 2, I take 2 away. So what does that give me? That gives me 0 here for the x, and negative 2, and then my y, 1 subtract 2, negative 1 subtract 2. These are my two new coordinates of my key points. So let's see if all that works. 0, negative 1, that fits. So I can see right? That's my first section. And what about -2, -3? Here we go. There. Now, what if you're given this? I think we're really comfortable with the other style when you're just given one polynomial expression on top of the other. Let's say the exam comes along and you're given this and you're stumped a little bit. If you prefer the other way of graphing, like just using asymptotes and non-permissible values, this is where we're headed today, by the way. Watch this. Let me do number 1. I just want to show you the links, right? So you can just watch this, because this will be on the video later too, if you want to record it better. All right, this is a rational expression. Okay, it's rational because there's a variable on the bottom. And what we're going to do today, we're going to do a little work with rational expressions. So what if I wanted to combine these two guys? I'd need an LCD, right? Because they're fractions. So what would my LCD be? It'd be x plus 1. Agreed? Okay, so if I wanted to combine these two guys, I'd have to do this. I'd have to do x plus 1 on the bottom, and then I'd have to do the same on the top so it doesn't disrupt the value at all. So now I can combine these on 1, and I get 2 times x plus 1 all over x plus 1, right? Because that's the whole purpose of common denominator, so I can push two terms together. So then what do I end up with? I get 1 minus 2x minus 1, agreed? Finally, I get minus 2x over x plus 1, okay? Oh, sorry, minus 2. Oh, glad you guys are with me today. Okay, agreed? All right, so minus 2x, 1 minus 2, 1 minus 1. Okay, so now, let's see, I guess I could factor a negative out of here, but that's not really going to help me much. But could you graph, what if I gave you this function to graph? What would you say to me that graph, what that graph looked like? What are the key parts of this graph? Non-permissible value, x equals -1. Vertical asymptote, x equals -1. Horizontal asymptote, y equals -2. X-intercept, let's see. Put a 0 in for y. 0 equals, the bottom just disappears, minus 2x minus 1. 2x is -1. X is -1/2, right? Okay, so that's my x-intercept. What about my y-intercept? Put a 0 in for x's. All the x's disappear. -1 over 1. -1. Okay? Sorry, guys. Agreed? Is that all the info? Okay, well, let's see if this graph lines up with this. Let's see. Non-permissible value, -1. Sorry, I don't know how I'm going to do this. Maybe fold it. Okay, let's see if this works. Y-intercept, so the asymptotes match. Y-intercept -1, x-intercept -1/2. That's it, right? It's the same graph. It's the same function. I just put it in a different form. So if you get a function in this form, and you can just graph using transformations, great. If you don't want to use this style, you can certainly just combine them and use this style. Does that make sense? Yeah? It's the same function. I'm just showing you that there's two styles you might be given. Okay? Can I push your boundaries a little more? Okay, let's say I start with this. By the way, how many people look at these types of rationals and can make sense of it, like have graphed from this style before? Adam, you guys? Okay, so if you like this style, and you don't like what we've been doing in class for the last couple of days, this is a polynomial, agreed, divided by another polynomial. Have you ever done polynomial division? Yeah. So remember we did that in, okay, so you could divide this through. X goes into there. I'll show you the long way, right? Like, so we'll just do, so I'd have to do a minus 2 here, so that would give me minus 2x minus 2. I do my subtract, that disappears. Negative 1 plus 2 gives me remainder 1. So, negative 2x minus 1, all divided by x plus 1, gives me a quotient of negative 2. And what's my remainder? My remainder is 1, and that 1 gets expressed over x plus 1, right? So I could also say then y equals 1 over x plus 1, take away 2, right? So I just converted this back into this form, right? You can work backwards and forwards between two forms. You know, if you have the time, right? So if you like this style, graph from this style. You can just do your long division, and you can always convert it through long division into this style. I think the key is being able to graph from either form you're given, right? I think that's really key. So here, let's look here. Could we do this transformationally? Let's see what happens here. What do your eyes see here? Shift left 3. Shift up 2. So this affects my asymptotes, right? That means vertical asymptote x equals negative 3. Horizontal asymptote y equals 2. Okay. And what else do you see? There's one other thing. A reflection, right? Reflect over. So the whole function sort of reflected, so that would be x-axis, right? Okay, so that's unusual. Let's see if we could do this. I think it's a little harder, to me it's a little harder doing this way because it doesn't seem like you're given as much info, but I guess we should do intercepts, right? X-intercept, y-intercept. Okay, what would the y-intercept be? Negative 1/3 plus 2. So what is that? 1 2/3. Okay. The x-intercept, I put a 0 in for y. Negative 1 over x plus 3 plus 2. I'll move this term over maybe. 1 over x plus 3 equals 2. Sorry, I should have given myself more room. Cross multiply. 2x plus 6 equals 1. 2x equals negative 5. So x equals negative 2.5, right? Negative 5 over 2. Okay, so let's try. We'll do this last one together, then I'll leave these two with you to do for kind of practice work. So let's do a vertical asymptote negative 3. Horizontal asymptote is a positive 2. My x-intercept is negative 2.5. So negative 1, negative 2, negative 2.5. And my y-intercept is 1 2/3. So 1 2/3 about here. Okay, so I think I clearly know what's happening over on this side. I just don't know what's happening on this side. I know it's going to be diagonal because it's one of the classic parent graphs and they operate diagonally. So I guess I'll do a test point. I'll do negative 4. So y equals negative 1 over, I guess negative 1 plus 2. So that would be 1 plus 2, 3. So when x is negative 4, y is 3. So I think I'm pretty confident, just asymptote, asymptote, okay? It's just another way to look at rationals, right? But it's the same, like I said, it's just a different form. And again, I'll bring it back to you're quite comfortable with this with quadratics, right? Because you're graphing from this form, right? You should be able to graph from that form. You could use table values. You probably move this form into vertex form, unless it's factored, right? You could factor this, get your x-intercepts, and graph that way, get your x and y-intercepts. You also are comfortable with this form, right? You're going to let graphing quadratics from this form. So just two different styles of being given a quadratic. This is two different styles of being given a rational. But like I say, just like you can always convert and move back and forth between forms, you can do the same thing with rationals. And you have the skills. Okay, I did ask for the clock to be fixed, but it's not yet, so we have lots of time though before break. So I'm going to leave those with you too, so you can practice on that form, all right? And let's move over to rational equations. So in your notes, if you looked in your book last night, it talked about rational equations. Just to refresh your memory, a rational equation, we're not graphing anymore, so there's no y equals. You have just two expressions on both sides. So this is on page 123. So a rational equation is an equation with variables in the denominator and an equal sign. Okay? They can be simple, they can be more complicated, but the end game is just like every other equation, you're solving for x, right? You're trying to solve for x. The only thing is, we know in rationals there's non-permissible values. So just like when we were graphing, you should always figure out, first of all, what your non-permissible values are, and you're going to have to sort of do a checking your work, just like you did with radicals, right? You want to make sure that none of your answers are non-permissibles. So how do we solve a rational equation? Well, first of all, you're going to identify your non-permissibles, right? And I'll just give you non-permissible values. You do the same thing. And then you have to choose your LCD. Do you kind of remember doing this? Like if I look at this baby one, this baby equation here, what would the LCD be for that equation? 3x, right? The LCD is 3x. And just like you did before, but maybe it's been a while, so you might not remember, we kind of use the LCD in a unique way. We multiply every term by the LCD, because what that does is it gets rid of your denominators. Right? And we'll see that in a sec. So if I do that, it simplifies the equation, because then I'm just left with a linear equation or a quadratic on one line, and it's easily solved. The reason you can do that in math and it doesn't affect anything, if you're multiplying every term by the same value, you're not changing the proportions. The proportions are all the same. You might get a larger answer in the end, but when you simplify your larger answer, it'll simplify down to like the correct answer, because you're not changing the proportion of anything. You'll still get the right answer. So it says identify non-permissibles, multiply each by the LCD, solve the equation, and then just check to see if any answers must be rejected, right? Because you're checking back in your non-permissibles. So if we just do a real quick refresher, and then we'll do some of the other ones that I've given you on that page. So if we do this example that they've illustrated up there, 2 over x equals x plus 1 over 3. All right, first thing I do is identify my non-permissibles. Yeah, x can't equal 0, so I got to keep that in mind. And now, what's my LCD? Well, we've already identified it's 3x. So what happens is every term, now here there's only 2, one on each side, but every term gets multiplied by 3x. Because what happens is, if you multiply by the correct LCD, your denominators should always cancel out. Okay? Which is lovely, because then you don't have to deal with fractions anymore. So I'm left with 3 times, this is what I'm left with, 3 times 2 equals x times x plus 1. All right, so that's easily solved. I get 6 equals x squared plus x. So this one resulted in a quadratic. That's okay. We know how to solve quadratics. 0 equals x squared plus x minus 6. I'll move over here. This one factors, right? X plus 3, x minus 2. So x is negative 3 or x is 2. Now I'm going to check back to my non-permissibles. Neither are non-permissible values, so those are my solutions. You good? Questions at all? All right. Flip over the page I gave you, and we'll do a few more examples, just to get all the cobwebs dusted off for, and then there's a few more. I'm going to get you to solve those last 2 graphing questions, and then you can, there's a few examples in the book, and then I'll tell you what else you can work on today. All right. So again, all the instructions are reiterated again. So it's on the second side of that graphing thing I gave you. State all non-permissibles, multiply each term by the LCD, solve, check your answers. All right, so these are not that challenging, but they go through the steps for you. All right, what's the non-permissible value again? 0. And what's the LCD? X. Okay, so every term gets multiplied by x. So I get 2x equals, oh, no, it's here. All right, what's going to happen over on this side? 20 minus 3x? Well, if I had an x here, right, and I'm multiplying by x, those guys just cancel out, right? So if you're really good at this, and you remember, you don't actually have to show that step. You could have just shown me this, right? That you knew the denominator canceled out, if you want, okay? So this is a really easy one, right? 2x equals 20 minus 3x. Add a 3x, so I'll get 5x equals 20. X is 4. That's not a non-permissible, so that's it. I'm good. Johannes, you'll need this. Okay, what about the next one? Non-permissible. X can't equal 2. What's my LCD? X minus 2, right? Okay, so I'm going to give you a sec. See if you can pull this one off. While you're doing that, I'll hand out the... Oh, they've erased the number again. I don't know why someone erases it all the time. But yesterday's winning number was 2085525. so hopefully you've had time to look at this one. So my LCD is -2. Every term has to be multiplied by -2, right? So if that happens, I get x squared. So this term has to be multiplied by x minus 2. X has to be multiplied by x minus 2. And 6 has to be multiplied by x minus 2, right? Now, if you didn't show this, if you just kind of had these canceled in your head already and led with the x squared, that's fine. But see what happens here? There's only one denominator, that's going to be eliminated. These two have to be multiplied by the x minus 2, so I get an x squared equals x squared minus 2x. And then, what am I going to get? Negative 6x, positive 12. Okay. So my x squareds actually cancel each other out. So I'll get 0 equals negative 8x plus 12. 8x is positive 12. So x equals 12 over 8, 3 over 2. If I simplified? Here. Yeah, either. You could even leave it as 12 over 8, actually. Are we good? Okay, what about this one? Little slightly more complicated LCD, I think. Non-permissible values. Oh, I should check my non-permissibles, but it's fine, right? Non-permissible value. X can't equal 0 or negative 3, right? Okay. What's your LCD? Yeah, I need the x, and I need the factor of x, and I need the factor of x plus 3. I need both of those factors, or my denominators will not be eliminated. So give that one a try. Come up with a solution, anyone? What'd you get? Negative 6 over 5. Did anyone else get negative 6 over 5? Yeah, so it sounds like that's a good one. So every term is going to get multiplied by x, x plus 3. So that means my 1 is going to be multiplied by x, x plus 3. When I multiply this next term, the 2 over x, the x's cancel. That leaves me with just 2 times x plus 3, agreed? And then my last term, I'll just get an x times an x, right? Because the x plus 3's will cancel. So here I get x squared plus 3x plus 2x plus 6 equals x squared. Another kind of nice one for us because the x squareds cancel, so we don't have to deal with the quadratic. I get 5x equals negative 6, x equals negative 6 over 5. That's not one of my non-permissibles, so the answer is good. Okay, next one. This gets a bit trickier. You've got 3 denominators. So the non-permissible is easy. I think it kind of jumps right out at us. Negative 2, right? Now, LCD, the lowest common denominator means lowest, right? The smallest. It's always the easiest to deal with because the smaller you can keep your numbers, the easier it's just to do the math. Same as avoiding negatives whenever you can. But even if you don't choose the LCD, the lowest, it'll still work out if you pick just a common denominator, right? One of the ways that you can pick a common denominator is just including all of them in there, right? But it's not necessary usually to include all of them. So what would be the lowest common denominator? Close. The lowest common denominator, that they would all cancel out with would be 4 times x plus 2. You'd have to need more than the 2 because if you just use 2, the 4 wouldn't cancel out on the bottom, right? You need it at least as big as your largest terms, right? So my LCD would be 4 times x plus 2. Did anyone use 8 times x plus 2? Use the 2 and the 4. That would still work. You would just end up doing a lot more reducing at the end. But you must include at least the 4. Okay, so now what happens here? Okay, if I multiply every piece by 4 times x plus 2, my x plus 2's disappear, and I'm just left with my 4 times 2 minus, okay, what happens here? The 2 cancels out, but that leaves me a 2 on the top and an x plus 2. Agreed? Mm-hmm. Equals negative 3 times x plus 2. Right? So stop me if you have any questions, because I can go over this one in a little more detail if you need it. So let's see, 8 minus 4 is 4. 4 minus 2x equals negative 3x minus 6. I'll move my 3x over to give me a 1x. And I get x is negative 10. It's not a non-permissible. So I'm hoping that's a good answer. Everyone okay with that? That would be the lowest common denominator, right? Are we good, or? Okay, what about this last one? Take a close look, see if you can figure out your non-permissibles and your LCD. Okay, who wants to give me some non-permissibles? Sorry, pardon me? Positive and negative 1. Agreements or? Did you do anything, Eduardo, before you figured out your non-permissibles, or you just kind of looked at, set everything equal to 0?
Factored everything.
Yeah, I think factoring's the key here, right? Anytime you can factor, you want to, because that also helps you figure out your LCD, right? So I would have factored, this becomes a 2x minus 1. This is my difference of squares, right? X plus 1, x minus 1. And this becomes 3x minus 1. Okay, so that helps me figure out my LCDs for sure. Because my LCD, I have to include each factor at least once. That's going to give me LCD of x minus 1, x plus 1. Yeah, and the 2 times the 3, right, which is 6. Okay, and you could leave it as 2 times 3 if you want, if that makes things easier for you. Okay, if I kind of do it my quick way, because I think, you know, we're in grade 12, we should be able to sort of do that. Let's see what happens here. So for my first term, I'm going to be left with my 5 times the 2, and here's where you might want to leave it as, you want to think about it this way. You could leave it as 2 and the 3, right, and the x minus 1 and the x plus 1 in separate pieces, because it might help you a bit. So the 2 and the x minus 1 get canceled out. That leaves me with 3 and x plus 1, right? Then I have my equal sign. Then I have my next 5. So the x minus 1 and the x plus 1 cancel, so that leaves me with the 6. And then my last term, the 3 and the x minus 1 cancel, so that leaves me with a 2 and an x plus 1. Okay, so now it's basically keeping organized, right? So I have 15x plus 15, whoops, equals 30 plus 10x plus 10. So I have 15x plus 15 equals 40 plus 10x. And then I get 5x equals 25. X is 5. Just do a quick check back. That's none of that is, or that one's not one of my non-permissibles, so that should be my answer. Okay? Okay, so that's your, I guess, reintroduction to rationals. It is something you did before, I think, in the grade 11 course, for sure. So, you know, peck your LCD, multiply each term by the LCD. That should make all your denominators disappear. So you're left with either a linear or a quadratic to solve, and then just check your answers with the non-permissibles. It's pretty straightforward. Now, the solutions to a rational equation, if I were to graph this, like if I put this all on one side and graphed it, the x-intercepts, right, would be the solutions to a rational equation. That's how those match up all the time. Okay, your long past break time is 1:03, so we'll take a break if you need it. When you get back, I'd like you to, if you didn't already, finish those last 2 little graphing questions on the flip side of that paper, right, just to get practice from that version if you like. And then there's an assignment on rational equations, and then you can start the chapter test in the book too. And I'll have a bit more review for you to do as well tomorrow, and then we might even start, I might even hand you out the new stuff on Friday. We might start the new unit Friday, but the test won't be till Tuesday. So you got most of the next part of the class to work, ask questions. Yeah. in here.